Rather than try to talk through all the different announcements that I have, I'm going to send out an email. It'll talk about short homework assignment for Monday. It'll talk about final exam. It'll talk about review session on Wednesday. And all related things like that. So we do have class Monday. We will have short homework due Monday. We will have a review session Wednesday, and our final exam is Thursday night. And so I'll send that email out, and I'll put it all on Blackboard announcements, all the details about our final week here, okay? So we are talking about, and this stuff we do today and Monday is stuff that's on the final, so this is important stuff. So we're talking about the arcsine, or the inverse sine function. And so if f here, if f is, we're calling f sine x, then our f inverse function for f is called arcsine or inverse sine. Arcsine or inverse sine. So based on being experts at the sine function, knowing exactly what the input is and exactly what the output is, then what would the input and output of arcsine be? So the idea of an inverse function is what?
You reverse the input and the output.
Yeah, it's the reverse process, right? So what came out of our original function now becomes the input, and it cranks the reverse function. So it'll, given the output of the original function, it'll give the corresponding input of the original function, right? So it's the reverse process. So what would the input of arcsine be? Vertical distance above horizontal diameter. Good. Anything else? Yeah, this is key. This is key. In radius lengths, right? Because we know that's the output of sine, so it's the input. Okay, in radius lengths. So what are the potential values we could put into the arcsine? If it's this, if it's the vertical distance in radius lengths on the circle, of a point on the circle, so what's that? No, so what I'm asking is what potential actual numbers would work? Could we plug in any number into that? So what's the least value that we can have for a number of radius lengths below the vertical diameter?
Negative the radius. The radius.
But in radius lengths. So what would it be? Negative 1, right? So we can't put negative 1.3 into this. It'll refuse it. It'll say no, it doesn't work. All right, and we can't. What about what's the greatest number of radius lengths we can be? The top of the circle we could be 1. So what goes into arcsine has to be between negative 1 to 1. Just like what comes out of sine is always from negative 1 to 1. Okay. What about the output of inverse sine? So we're going to put the vertical distance in, and that's what I'm showing on this graph here. We're going to put vertical distance in. That's represented by the red line. Okay? The red line represents some vertical distance, right? And what's arcsine going to give us? What goes into sine is what's going to come out of arcsine. Angle? Good. Good. Excellent. Okay, so that's key. So the very first thing we got to learn about arcsine is that what goes in is a vertical height. What arcsine is going to give us then is a corresponding angle. Okay, but then we notice, like, look at this example here. F inverse of radical 3 over 2, right here. So this is the arcsine, or the inverse sine of radical 3 over 2. So what kind of number is radical 3 over 2? What kind of number is radical 3 over 2? Is it a radius? Is it a volume? Is it a what kind of number is it? It's a radius. Is it a radius? What is it? Radius length. Which radius length? Vertical distance and radius lengths is what goes into arcsine. So I'm going to set that up here. Radical 3 over 2. That was one of our y coordinates on our unit circle on the special angles, right? On the key angles. So here's radical 3 over 2. So what's the output going to be? So if we input a vertical distance of radical 3 over 2, the output's going to be? Okay? The angle swept counterclockwise from 3 o'clock. What is it? What's that? Oh, no. Like, this is why we learn the unit circle. We want exact values. Exact values. What exact angle gives us an exact vertical height of radical 3 over 2? What's that? He said pi over 3. Agree with that? Is that this one here?
But wouldn't it have two answers? Would it be pi over 3?
Okay, so pi over 3, yeah. He said wouldn't it have two answers? How about here? Yeah, so what's second quadrant angle? Wow, can we get, everyone got their homework in? Are we done? Okay. 2 pi over 3. So there's two answers. Agree with that? Let's look over on that. So here's my graph of sine. I got my graph of sine. So horizontal axis is angle. Vertical axis is vertical distance above the horizontal diameter. Let's take a look at that. What am I showing here? So zoom in.
Every time the vertical distance is radical 3 over 2.
What's that?
Every time it's radical 3 over 2. What you're showing.
Right. So are there just two results where the vertical distance is radical 3 over 2? What's that? For every period there's two, but is there any limit to how many periods we can run, right? So I can go around once, I can go around a second time, I'm going to get two more angles, right? I'm going to get these two, you see? And if I run a third period, I'm going to get these two. Every time I go around the circle, I'm going to get two more angles that give me that vertical distance. So the list goes on and on. Does it make sense that how I'm showing that for one vertical distance there are many angles? You just keep going around the circle, you're going to keep hitting those two spots, and you're going to get that same vertical distance over and over again. So this is in conflict then with our idea of function, because what's our idea of function?
There's only one out.
Given an input, one output. You can't get more than one output, or it doesn't have. If it only gives you more than one output, then it's like it doesn't know what its function is, right? It's ambiguous. Okay, it's gotta be predictable, deterministic, right? So put an input in, you're gonna always get that one output out. All right. So we have to think about this, because right now the way we're thinking about it, it's not a function. One vertical distance gives us many angles that achieve that vertical distance. Okay, so what do we do? What we need is so here's our possible inputs, right? We said that possible inputs could be from -1 to 1. So what we need to do is, for each value from -1 to 1, we want to get one angle. We want to get one angle for every value from -1 to 1. So in order to do that, we need to kind of like remove some or a lot of this graph, right? We just want part of this graph so that one y value gives us one angle in return. So what we need is some range, some convenient range of angle, such that every value from -1 to 1 corresponds to just one output angle. So what range of angles would meet that criteria? What's that? Okay, one period. Good thought to start. So I'll highlight one period here.
Here you give us two answers.
So that's okay. No, hold on a sec. Here's one period. So now let's take a look at it. Does it achieve our purpose of one vertical height gives one angle? Does it work? Does it work, say, for that one right there? Do we just get one angle in return? No, right? Because we get this angle here. And this angle here. Okay, but that's a good opening thought, all right? So it's the idea. The idea of it is we want some range of angle that just gives us, for every one from -1 to 1, every height, vertical distance from -1 to 1, we get just one angle in return. So do we want to adjust this or try something new? What's that? Quarter period. Okay, so what I'm hearing is like from 0 to pi over 2? All right, so from here to here. So now, for every value from -1 to 1, would it return one angle? For every vertical distance from -1 to 1, does it correspond to one angle? Yes or no? Yeah, it looks like we're missing negative values here, right? So it works for 0 to 1, we get just one angle. But now we have no angles for when the vertical distance is negative or below.
So if we do half of it, we're only starting from the quarter.
Okay, so there's some ideas here. Go ahead.
You do only half the period, but you start from the 1/4 mark, and you go down to the 3/4 mark. So you end up at the max, starting at the max.
Okay, so what I heard was this. Start here and go down here. Is that what I heard? All right, so that's been offered up from there to there. And what were you gonna say? Same thing. Does it work? Do we get just one angle for every input from -1 to 1? It works. Okay, but take a look at if we had the angle, if we had the vertical distance of 0. So right here at 0, what angle is it giving us? This choice. What angle is it outputting for a vertical distance of 0? She said 2 pi. Agree with that? Pi, right? So over here at pi would be where the vertical distance is 0. It'd be kind of nicer if when we had this vertical distance of 0, we had what angle? 0 would be a nice natural choice, right? So because 0 is our starting angle, so for a vertical distance of 0, it'd be nice to have an angle of 0. So that's why this works, but it's not very convenient because it's putting us over there from pi over 2 to 3 pi over 2, where a vertical height of 0 gives us an angle of pi, and we'd rather have 0. So let's go back to the blue one. How can we improve on the blue one? What's that? Okay, so that's what we do. So he said, go the other half, go negative. And so this is exactly what we do. We look at from negative pi over 2 to pi over 2. Does it hit exactly one angle for every vertical distance that we could choose? You see that? And it has the kind of the nice feature that when we're at 0 height, we get the angle 0. So this is the most natural choice, and so this is the convention that mathematicians have said. We're going to pick from negative pi over 2 to pi over 2 to be the range of angles. That's the output of Arcsine. It's the output of Arcsine because it gives us just one angle for every vertical height that we could pick.
It's a range of angles. Can you repeat that sentence again? A range of angles. I'm trying to write it down because I understood what you were doing this whole time, but I didn't necessarily know what you were doing for. It's like for the output.
Well, because the input is what? The input is vertical distance above the horizontal diameter, right? That's represented by that red line. And we need a range of angles such that we hit every vertical distance from -1 to 1 with just one angle, right? With just one angle. So this is the range that we pick, negative pi over 2 to pi over 2. That gives us just one angle. So look at that red line intersecting the highlighted blue over here. So I always get just one intersection for every red line that I can pick. And that intersection represents some angle. Okay, so which is it? So back to this question, radical 3 over 2. What is, now that it's a function, by restricting this range of angles, we've got a function. What is the actual single output for radical 3 over 2? Okay, so let me try to put it in place here. So for radical 3 over 2 is about just had it. Is about right there. Okay? So what is the true output of Arcsine, the one value? Okay, I heard pi over 2 and I heard pi over 3. Which is it? It's this angle right here, which is pi over 3. Okay, so, but we know that there's a lot more angles that are needed in the real world, not just these angles from negative pi over 2 to pi over 2. So that using the arcsine is just going to give you an angle between negative pi over 2 and pi over 2. Given your situation, you may have to adjust to figure out, what angle you have, which may not lie between those two in the context. Does it make sense? So there's some work to do. It's not just a matter of just a simple, hitting arcsine button on your calculator. There's some thinking involved because of this situation that we have. Okay? So let's do some examples here. So here I have a process, the arcsine of the sine of pi over 6. If we're going to do that process, what comes first? In that process, what comes first? Yeah, sine of pi over 6. So what's the meaning of sine of pi over 6? What does that mean, and what's its value?
It's the vertical height above the horizontal axis at for pi over 6.
Okay, so for pi over 6, right there, that's pi over 6. That right there is going to give us the vertical distance above the horizontal diameter, which is? Remember your unit circle. And I'm even kind of showing you there. We should know this, right? What is that? So here's pi over 6. We want the sine, which is the vertical height in radius lengths, 1/2. And now what does it say to do? Take the inverse sine. So given a vertical height of 1/2, sine inverse will tell us what? Which angle between negative pi over 2 and pi over 2 gives us that vertical height, which is? Oh, it seems so easy, right? Why can't, if we're going through a process and reversing it, then can't we just write down the starting value? Okay, not so fast. You try this one, okay? It's not that easy. So you try this one. Go through the process step by step, just like we did on that last one, and see what happens, okay? Because of this restriction on the angle range, you have to think it through all the way through the process. Go, see if you can do it. Sitting and waiting for me to do it in a second is not acceptable. You have to try. Work with somebody else if it's that unbearable. No calculator. Don't use your calculator. You should know these from the unit circle. There's your hint. That's your hint. Okay, what do we do first? Someone in the back. What do we do first? We're going to chase out this process step by step. What comes first? Yeah. And tell me what that means and what it is. Right? In? Agree with that? Square root of 2 over 2.
When you write the answer, do you have to put it in the sine inverse? Or do you just write 2 over 2?
This isn't the answer. This is the first step of the process. This is just sine of 3 pi over 4. All he's done so far is the sine of 3 pi over 4. That's all we've done. So now, and that's this, and what's the units? What is that measuring? Right there.
Radius lengths above the horizontal.
Radius, that's how many radius lengths we are up. Remember that number was about 0.7, right? Or 0.71, about. So we're 70% up the radius there, okay? So, arcsine of that. So now we're looking, now what's our input? Our input is vertical height and radius length, and the output of arcsine is? So the output is an angle, swept counterclockwise from 3 o'clock. Is it 3 pi over 4? No, what is it? It's pi over 4 because the output of sine inverse is in this range, negative pi over 2 to pi over 2. So we got this vertical height. For arcsine, it will give you this.
Is there a difference between arcsine and secant?
Yes. Yep. So this is, what's the answer to this? Pi over 4. Did you see what happened? So it's a really nice problem because it really forces you to understand what's going on with sine inverse. Anybody have a question? Does it make sense? To get the other side.
Yeah, it's because like because cosine starts at the max. Oh, never mind. It's a different.
But cosine is doing horizontal distance, right? We're going to get to it, but remember that's horizontal distance. Yeah.
And it's not always going to be, like, you can do problems that are off the circle. Like, you know how you have something really wild radicals? Or is it always going to be, like, simplicity, just the radius off the circle?
No, this doesn't have to be one of the ones we memorized. Is that what you mean?
Yeah.
Yeah, it could be any. I could have given you any angle through here, like 2.226 radians, or 162 degrees, or something like that.
And you would have to, how would you find the straight line?
So then you need to find the sine with your calculator. So you find the actual sine with your calculator, and then also arcsine with your calculator. But then know that arcsine is going to be, right? It's going to be in the first quadrant. It's going to be in the first quadrant. Okay, do this one. Go, do this one. Okay. What do we do first? Someone else in the back. How about this side, this back corner? What do we do first in this process? Save us. How about Nike hat? You know what we do first? Do we do arcsine or sine first? Okay. Do we know what sine of 5 pi over 3 is? So here's our angle 5 pi over 3. Okay. So we need that vertical distance in radius lengths. They're saying negative radical 3 over 2. Agree with that? So, okay. And then we're going to take, so now it's kind of like we start over with a new function, right? Now the new function is sine inverse. What goes into sine inverse? Vertical height, right? Vertical height above the horizontal diameter, which is? Negative radical 3 over 2. That's what's going into sine, and it's going to give us the output of 5 pi over 3, right? 5 pi over 3. Is it 5 pi over 3?
Yes.
No. You missed the point. Arcsine gives us an angle between, look at the blue, look at the highlighted blue. It gives us an angle between negative pi over 2 and pi over 2. 5 pi over 3 is way outside that range. So we're down here, right? So what angle from negative pi over 2 to pi over 2 gives us that vertical height? Negative radical 3 over 2. This angle right here. You see? That's the angle we need. Which is? Negative pi over 3. Is this making sense? You say no? Okay, so we got the sine of 5 pi over 3. I think we were okay with that. Radical 3 over 2. Now just forget about that. We just found that using sine, and you're going to look at this now as your input, this vertical height, and say what angle between negative pi over 2 and pi over 2 gives us that vertical height. So we're down here. If it's negative, it's got to be, if it's negative, it's here from negative pi over 2 to 0. Right? It's right here. This angle right here. Negative pi over 3. Okay, does it make sense? And if not, can you ask a question to clear it up?
Can you re-explain the right graph and red drawings that you drew?
Yeah, so the input now, since this is just a plain old sine graph, the input is the y and the output's the x, right? Input's y and output's x for arcsine, because this is sine. So our input is the vertical distance above horizontal diameter, which is our negative radical 3 over 2. What's that? Yep. It's the angle within the range that we established. So there's our input, and so we look here. Where does it hit our blue graph? It hits it right here. So the input will be the output of arcsine will be the x value that will give us that vertical distance. So the x value is right here, and this is our angle, negative pi over 3. Or this right here, right? This angle right here. Going like that. So whenever you have a negative distance above the horizontal diameter, you're going to get a negative angle for arcsine. Any negative distance down here is going to be a negative angle from negative pi over 2 to 0. Negative pi over 2 to 0. These are the easy ones, right? So if it's up here, you're going to get an angle between 0 and pi over 2. But if you have a negative vertical distance above horizontal diameter, your arcsine will give you a negative angle from negative pi over 2 to 0. Is it better? No, it's not.
When you see an arcsine graph, is it always going to look like that, or will they switch the y and x axis because the input and the variable?
Right. So again, I'm showing you sine.
Okay.
So input is now this, and output's this.
Okay,
so if you truly put the input and output right, it would look like this. Exactly.
I'm just curious. So when
No.
I see it in the future.
Yep. If you see an actual arcsine graph, so if you're going to plot arcsine, what is it? It's going to look like this. Okay, where this is your vertical distance above horizontal diameter, x input, and then your angle is your output. So y coordinate input, angle output. So it will look like that. Okay. Can you ask another? Is it okay? All right. Let's just briefly kind of look at the same thing for cosine. So what's the input into Arccosine now? What's going to be the input into Arccosine? Horizontal distance, right? Horizontal distance, which will have a range of what values? From what to what? Again, the least distance to the right of the vertical diameter we can be is? -1. The greatest that value can be? 1. Okay? So again, what do we need? We need a range of angles such that every possibility from -1 to 1 corresponds to just one angle. This one's easier. Okay, he suggested 0 to pi. Does it work? Does 0 to pi just give us one angle for every value one angle for every value from -1 to 1? No? So so there's 0 to pi. So given an x value, do you get just one angle? Do you get just one angle no matter what x value you put in? Yeah. That's it. 0 to pi. So what? For arcsine, we use the right side of the circle, from negative pi over 2 to pi over 2 to be the output. For Arccosine, we use, to get all x values from -1 to 1, we use the top of the circle. All angles from 0 to pi. Okay, practice. What's that? So I want you to find the Arccosine of the cosine of 4 pi over 3. Go. Arccosine of the cosine of 4 pi over 3. So you should have an image of what the angle 4 pi over 3 is. That's why we had you do the unit circle quiz, not just for that one day, but to remember it. Okay, 4 pi over 3. What's the cosine? So what's the cosine of 4 pi over 3? -1/2. It's the horizontal distance to the right of the vertical diameter. In this case, it's to the left at -1/2. Here starts the parade. Okay. What's the arccosine of -1/2? Okay, we're getting the hang of it. So now it's going to be that angle between 0 and pi that has that same horizontal distance. So what angle is that? 2 pi over 3. This angle right here has the same horizontal distance, but it's within our range from 0 to pi. So again, input into arccosine, -0.5, output, angle between 0 and pi that results in that horizontal distance. Okay, if you got a question, don't be afraid to ask. Can you ask a question? If you're Don't be afraid. Speak up if you need to. Can I erase? You guys good, or do you have a question? You good? What's that? Okay, how about arccosine of cosine of 7 pi over 4? Last one. 7 pi over 4. Maybe we can talk about that. We'll do that after class if you want. Let's do this one. Okay, so where are we at cosine 7 pi over 4? Positive or negative? Positive, radical 2 over 2. So that would be this angle here. 7 pi over 4 would be here, right? Be this angle right there. Gives us a horizontal distance of pi, or no, gives us a horizontal distance of radical 2 over 2. Right, from there to there. So this is where radical 2 over 2, and that's what I'm showing right here. Radical 2 over 2. What's the arccosine of radical 2 over 2? So now we're saying, now we have this horizontal distance. What angle between 0 and pi gives us that horizontal distance? That's what we're asking. Pi over 4. Right here, pi over 4. Or right here. Pi over 4 right there. Is it better?
Yes.
Okay, cool.
The cosines are supposed to be equal.
What's that?
The cosines are supposed to be equal.
Well, it's just the range from 0 to pi is a little bit, we're more used to that than working with the negative angles. And so yeah, for that reason, that you could be right. Okay, so let's do another example, quickly. Let's talk about the bug. Okay, so say the radius is 3 feet of the fan. The radius is 3 feet. and currently the bug is 2.5 feet above the horizontal diameter, what angle swept from the 3 o'clock position has the bug swept to get to this place in the second quadrant that's 2.5 feet above the horizontal diameter? Can you do it? So look, what we have something that's related to vertical height, and we want angle. So what function is like that? We give it vertical height, it gives us angle. What function is like that? Sine, cosine, arcsine, or arccosine?
Arcsine.
Arcsine. Input into arcsine is? What's the meaning of it? Vertical height in radius lengths. How many radius lengths up are we? 2.5? How many radius lengths up are we? 2.5. Tell me, how many are we? Over 3, right? That's how many radius lengths we are up. It's the fraction of the radius that 2.5 is. Okay? So, find that with your calculator. Find that value with your calculator. Make sure your calculator is set to radians. Or let's do degrees. Set your calculator to degrees. Okay? What'd you get? As soon as you get it, tell me. 56.4 degrees. So that's what the angle theta is, 56.4. Is it right? Okay, so what angle did it give us? The angle in which quadrant? Yeah, so we gave it this height right here. It didn't know where the bug was. It had no idea where the bug was. We just told it this height, and so it's going to spit out which angle? Yeah, the one in the range of arcsine, which is from negative pi over 2 to pi over 2. So it gave us this angle, 56.4 degrees. So the question is, can we use that to get the angle we want? So how can you use 56.4 to get the angle theta where the bug swept from 3 o'clock? No, the radians would still be here too. The radians was, I think it's one. Did anyone do radians? Yeah, I think it's 1.2056. What do you want to do? Subtract it from 180. Did you say that was awesome? So, why would that work? So, if 56.4 degrees goes up to here, then also, isn't this 56.4? So how do we get, then how can we see that, use that to get theta? Yeah. So the whole thing, half circle 180, and then we want to go backwards or subtract that 56.4 right there. So is it 123.6? Did you catch it? Does it make sense? So you see, so it's not just as easy as plugging the number into the calculator and having it get the answer for you, because you've got to understand arcsine and make the adjustment. You understand that, okay, it's the equivalent angle in the first quadrant.
What are we trying to find right now? We're trying to find
Theta. The angle swept from...
Oh, okay. I thought we were trying to find the arcsine, because then I was saying, why do we need to
No, the whole idea was to get this angle from the beginning. Theta.
That works with the radius lengths as well. The radians?
Radians. So how would you, in radians, what would you do?
Do 2 or a pi minus 1.
Pi minus 1.02. Or 1.206. Okay, does it make sense? Okay, so one more last thing to show you. So suppose right now the bug is, so new topic, important. Suppose the bug is 1.4 feet above the horizontal diameter. Okay? How many radius lengths is it above the horizontal diameter? If r is 3. How many radius lengths above the horizontal diameter? 1.4 over 3. And what does that ratio, 1.4 over 3, what does it have to do with the angle theta right there? How can we relate that number of radius lengths to the angle theta? What does that equal in terms of theta? So right now we've got the number of radius lengths above the horizontal diameter. What does it have to do with theta? We should all know this, everyone in the room. Please. What does this ratio, which is the number of radius lengths the bug is above the horizontal diameter, have to do with theta? Or how can we express it in terms of theta? Arcsine of theta. Sine of theta. What's that? Arcsine and sine are the same thing? No. So,
That's not what I'm saying.
okay. What do you say the answer is? No, it's okay. What do you say the answer is? Sine of theta. Right. The number of radius lengths above the horizontal diameter is sine of theta, right? Okay, so now watch. I'm going to make a triangle out of this. A right triangle. No, it's not a 30, 60, 90. It could be any triangle. Okay? It's going to make our right triangle right there. So what is this length right here? 3 feet. So notice that what we just set up was, so relative to this angle theta, if we set up the ratio for number of radius lengths above the horizontal diameter, 1.4, we call that the side opposite of theta. And in this right triangle, what's this radius called? Hypotenuse. So many of you have learned this relationship before. But the point is, this preserves the idea that sine is the number of radius lengths above the horizontal diameter, because the opposite side is how many feet it is. To get radius lengths, we're going to divide by the radius, which is the hypotenuse of the triangle. Similarly, whatever that is, so what does the cosine equal in terms of these measurements? No, in terms of these measurements, the cosine is going to be the horizontal distance in radius lengths. So you take that feet and you divide it by 3 feet to get the number of radius lengths. X is called?
The adjacent side.
X is called the adjacent side because it's next to the angle. And 3 is still the hypotenuse. Jeez, could you just wait 30 seconds, dude? Okay, so this is what we're going to be doing Monday. Really important for the final. Okay? So sine is opposite of hypotenuse. Many of you have heard that before, but it preserves the idea of vertical distance and radius lengths. Cosine is adjacent over hypotenuse. Again, preserving the idea of number of radius lengths to the right of the vertical diameter. Okay? I'm going to send out an email and post something on Blackboard with all the information about next week. Okay? Have a good weekend.